So, picture this. You're sitting at your desk, just sipping your coffee, minding your own business, and suddenly you are handed a critical file.
Oh, the classic developer nightmare.
Right. The platform team is totally overloaded, the deadline is super tight, and you're the only one available. So you open the file, and your stomach just completely drops.
Because it's written in something completely alien.
Exactly. It's written in a programming language you have absolutely never used, not even once. The syntax is weird, the structure makes zero sense, and you are expected to not just read it, but to actually add complex new logic to it?
And, without bringing the whole system crashing down, it is a uniquely terrifying modern experience.
It really is.
It's kind of the developer's version of being asked to land a commercial airliner when you've only ever played a flight simulator on your laptop.
That is the perfect way to put it.
Oh.
And honestly, in the age of AI, this exact scenario is happening to you, the lifelong learner, more and more every single day.
Yeah, we lean on AI heavily to bridge these massive knowledge gaps.
We do. But how safe is that bridge, really?
That is exactly what we're exploring in today's deep dive. We are looking at a really fascinating narrative piece by Aaron Rose. It's called The Secret Life of Claude Code, the language you don't know.
It's a remarkably insightful piece, I have to say, because it grounds this very abstract problem in, well, in a very human story.
Yeah, it's framed as this narrative taking place in a grand, quiet Victorian library in London.
Right, and we follow these two software engineers. There's a junior developer named Timothy and his senior colleague, Margaret.
And the mission of our deep dive today is to extract the exact strategies Margaret shares with him. We really want to unpack the specific toolkit you need when you are partnering with AI to code in unfamiliar territory.
Because you definitely need a toolkit.
Oh, absolutely.
Right.
But even more importantly, we are going to discover where the safety limits of that AI partnership actually end. Because, spoiler alert, they absolutely do end.
They definitely do. Okay, let's unpack this. Let's look at Timothy's dilemma. He has been handed a file written in Go, which is a language he doesn't know at all.
Right.
And he needs to add this retry logic to a service that relies on some pretty complex concurrency. We're talking things like coroutines, channels, and wait groups.
Yeah, and we should probably pause right there and just define what those terms actually mean.
Yeah, that's a good idea.
Because if you aren't familiar with Go, that just sounds like a list of random sci-fi words.
Yeah.
So concurrency is essentially doing multiple things at the exact same time and coordinating all those parallel tasks.
Right.
Think of a coroutine as an independent worker in a massive warehouse. You can spin up thousands of them, and they all just run around doing tasks simultaneously.
Okay, so if the coroutines are the workers running around, what are the channels and the wait groups?
So a channel is basically the conveyor belt connecting those workers. If one worker needs to, hand off a piece of data to another worker, they put it on the channel. And a wait group is essentially the warehouse manager holding a clipboard. They make sure every single worker has actually finished their shift before turning off the lights and locking the building.
Which sounds incredibly chaotic to manage.
It is. If you don't know how to operate the conveyor belts, or if that manager loses track of even one worker, the whole warehouse either grinds to a halt or workers start literally crashing into each other. It's notoriously tricky to get right, even for experienced Go developers.
Okay, so Timothy is staring at this highly complex warehouse system, and he does what any smart developer would do today. He doesn't panic. He just asks Claude Code to explain the file to him.
Yeah, a very logical first step.
And Claude absolutely nails it. It gives Timothy this perfect, lucid explanation of what's called the worker pool pattern.
Right.
So Timothy reads the explanation, he looks at the code, and he thinks, hey, I actually understand this. But he still hesitates to actually write the new code.
And Margaret, the senior engineer, she tells him that his hesitation is exactly the right instinct. She acknowledges that, yes, the AI gave him a genuinely valuable model of the code's intent.
Yeah, it wasn't wrong.
Not at all. The reason AI is highly reliable at explaining this specific thing is because Go's concurrency model is a very mature, incredibly well-documented pattern.
Right, it's seen it a million times.
Exactly.
Yeah.
The AI has read millions of lines of open-source Go code. It knows exactly what a worker pool looks like and how it's been supposed to function.
But, and this is the trap, understanding a pattern is entirely different from implementing it.
Completely different.
It's like reading sheet music without actually knowing how to play the piano. You can look at the page, you can understand the tempo, you can see where the notes rise and fall.
You might even hum the melody in your head.
Yeah. But if you sit down at a grand piano and try to physically play the song, your hands are going to freeze. You just don't have the muscle memory.
That's a great analogy. Margaret actually refers to this as a lack of instincts.
Instincts, right.
Yeah, when you are coding in a language you know intimately, you've developed this sort of sixth sense over thousands of hours of just making mistakes. You feel the grain of the language.
Look, when something just looks off.
Exactly. If you see a bad variable name or a return value being silently ignored, it physically bothers you. A red flag goes up in your mind before you even consciously process why it's wrong.
But when you're looking at a language you don't know, like Timothy looking at Go, everything feels equally plausible.
What's fascinating here is that, to a novice, AI output looks completely identical, whether it is flawlessly, elegantly correct, or dangerously, catastrophically wrong.
Wow. Yeah.
As Margaret says, you look at the code and you don't see logic. You just see shapes. You have absolutely no internal calibration for confidence.
You're just nodding along saying, yep, that sure looks like code to me.
Pretty much.
So if you lack that instinct and you literally cannot trust your own eyes, what do? I mean, how do you protect yourself? This transitions us to the tangible tools Margaret gives Timothy, the 3 technical safety nets.
Right, the safety nets. The first one is the compiler. Go is a statically typed compiled language. What that means under the hood is that before the code ever runs, the compiler parses everything you wrote and builds an abstract syntax tree.
Okay.
It checks strict rules. So if the AI hallucinates and produces code that is structurally wrong, like trying to send a text string down a channel that is only designed to carry integers, the compiler is going to catch it. It simply will not run the code.
But wait, compilers are just checking grammar, right? It's basically a spell checker.
That's a fair point.
Because a spell checker doesn't know if my sentence is a lie. It just knows I spelled the words correctly and put a verb next to a noun. So relying on the compiler to guarantee the AI wrote safe code feels, I don't know, incredibly dangerous.
And that skepticism is entirely justified. It's actually a critical distinction Margaret makes in the text. The compiler catches type mismatches and grammar errors, but it completely misses what she calls life cycle errors.
Life cycle errors. What exactly does a life cycle error look like in this context?
Well, let's go back to our warehouse analogy.
Okay.
Let's say the AI writes a coroutine, a worker, that starts up and waits for a box to come down the conveyor belt, the channel. But due to some subtle logical flaw in the AI's code, that specific conveyor belt never actually gets turned on.
Oh.
The compiler looks at that code and says, the grammar is perfect, ship it.
Because structurally, a worker waiting at a belt is a perfectly valid setup.
Precisely. So the code compiles cleanly, it runs without any immediate complaints. But in the background, that worker's just standing there, permanently blocked, waiting for a box that will literally never arrive.
Oh, wow.
Yeah, it never terminates. That is the coroutine leak. And it will sit there silently consuming memory resources.
Yikes.
So if your service spins up a new worker for every incoming web request and none of them ever terminate, your production server will quietly eat up memory until it's under heavy load and suddenly the entire system crashes out of nowhere.
That is terrifying. So the compiler catches bad grammar, but it is entirely blind to behavior. It doesn't know if the code is actually doing what the business needs it to do. So if the AI built a perfectly safe, grammatically correct bridge to nowhere, how do you catch that before you deploy?
This leads to Margaret's second safety net, which is strict secondary tooling. She specifically tells Timothy to use 2 built-in Go tools as a matter of habit. First is GoVet.
GoVet.
Yeah. While the compiler just checks if the code is legal, GoVet is a static analyzer. It looks at the code structure to find suspicious constructs that are technically legal, but statistically very likely to be bugs. It catches things like formatting errors in print statements or unreachable code.
And then there's the second tool, the race detector, right?
Yes, running tests with the strace flag. When you run go test trace, the Go runtime does something really fascinating. It actively shadows your memory variables during execution. It monitors the code for concurrent access patterns that could cause race conditions.
I've heard that term a lot. How does a race condition actually happen at the system level?
Okay, imagine 2 of our warehouse workers are told to update the exact same tally on a single whiteboard at the exact same time. Worker A reads the tally as 5 and gets ready to write 6. In that exact same microsecond, worker B also reads the tally as 5 and gets ready to write 6. They both write 6.
But the total should be 7.
Exactly. Because their timing overlapped, data is lost. The outcome changes completely depending on which worker wins the race to the whiteboard.
Ah, I get it.
It causes incredibly unpredictable bugs that are almost impossible to reproduce. So the race detector actively tracks those read and write collisions at runtime and flags them. It acts as an invaluable second pair of eyes when your own eyes just can't spot those timing issues.
Okay, so we have the compiler checking the grammar and the tools checking the logic flow. But neither of those tools actually knows if your code solves the original problem.
Right.
Which brings up the third safety net, and this one is all about executable specifications. Margaret tells Timothy that before he touches a single line of code, before he even thinks about asking the AI for the new retrial logic, he needs to run the platform team's existing tests.
Yes. Run them first to ensure they all pass.
Yeah.
Then, after every single small change you make, run them again. When your own judgment is blind, those tests act as your early warning system.
It sets up a baseline of truth. Like, if you break something you don't fully understand, the tests will scream at you immediately.
Exactly.
You cannot accumulate unverified changes when you don't have the instinct to know if those changes are even safe.
You're establishing a very tight feedback loop. AI generates code, the compiler verifies the types, GoVet and the race detector verify the concurrency safety, and the test suite verifies the business logic.
That's a solid defense. But, the tools can check your work, but how do you actually use the AI to write the new code without just blinding yourself again? I mean, how do you instruct the AI?
This requires a fundamental shift in how you interact with the AI. Before Timothy asks Claude to write the retry logic, Margaret tells him to ask the AI to teach him the language feature first.
So don't ask for the solution right away. Here's where it gets really interesting. The specific prompt Margaret suggests is brilliant.
It really is.
She tells Timothy to ask Claude, how does error handling work and go? What are the common mistakes developers make when implementing retry logic with coroutines? And show me a minimal executable example.
Let's break down why the mechanics of that specific prompt are so highly effective. By asking for a minimal executable example, you are forcing the AI to create a safe, isolated sandbox.
A sandbox, right.
You have a tiny, maybe 20-line piece of code that you can run, observe, and deliberately break, all without touching the real complex code base.
It's like you're learning how the keys on the piano feel before you try to play the symphony.
Yes.
And if you don't do this, you fall into the trap of treating the AI like a vending machine. You put your problem into the slot, press the button, the AI dispenses a block of code, you paste it into your editor, the tests pass, and you just move on.
And you've learned absolutely nothing.
Nothing at all.
The next time you encounter a Go routine, you will be in the exact same position of ignorance.
And it's actually worse than that. If the vending machine drops the wrong snack or, the gears jam, you don't know how to open the machine and fix the mechanism.
Right.
You just end up kicking the glass, or in a developer's case, blindly prompting the AI over and over, hoping it just magically fixes itself.
Which is so common. Margaret advocates for a completely different relationship with the tool. You have to treat it as a patient tutor who just happens to also write the code.
A patient tutor. I like that.
When you ask it to teach you first, you build vocabulary. By the time you finally do ask for the full implementation, you actually have enough vocabulary to evaluate the shape of what it hands back to you. You understand the why behind the code, not just the what.
But even the most patient, brilliant tutor in the world has blind spots.
Yeah.
And Margaret is very honest with Timothy about what Claude Code fundamentally cannot do. The AI has profound limits, especially regarding judgment, context, and scale.
That's right. Claude can write technically correct, highly idiomatic Go code. It can explain patterns beautifully, but it completely lacks judgment. Yeah, judgment is understanding the unwritten rules. The AI doesn't know the specific idiosyncratic conventions of your company's platform team. It might suggest a concurrency pattern that works perfectly in a small, isolated microservice.
Sure.
But if you drop that exact same pattern into a system handling millions of requests, it will catastrophically fail at scale. The AI produces good Go. It does not necessarily produce their Go.
The piece gives an incredibly vivid example of this limitation, specifically around the retry logic Timothy is trying to build. If you just ask the AI to build an exponential backoff for failing workers, wait 1 second, then 2 seconds, then 4 seconds, the AI will write that perfectly.
Yes, it will.
But if you have a massive system and 100 workers all fail at the exact same time, they will all wait exactly 1 second and then retry simultaneously. Then they will all wait exactly 2 seconds and retry simultaneously again.
They synchronize.
Exactly. It's like 1,000 people trying to sprint through a single revolving door at the exact same millisecond. They hit the downstream service in these massive synchronized waves, and they just crush the server.
Total bottleneck.
To prevent this, you have to add what's called jitter.
Jitter is essentially introducing a tiny bit of random mathematical variance to the backoff timer. So instead of everyone waiting exactly 2 seconds, one worker waits 2.1 seconds, another waits 1.8 seconds.
Right.
The retries spread out evenly over time, like an orderly line instead of a stampede.
But here's the catch. How exactly does one tell an AI to write jitter? You wouldn't even know to ask about it if you hadn't provided the proper context in the first place.
And this is Margaret's golden rule for prompting. Always give the AI context. You don't just ask for retry logic. You provide concrete parameters.
Like what?
You tell the AI, I have 50 concurrent workers reading from a channel. The upstream timeout is 10 seconds. Write retry logic with randomized jitter to avoid a thundering herd problem on the downstream ATI. The correct implementation changes entirely based on those specific constraints.
So vague requests get vague answers. If you give the AI a generic prompt, it will give you a generic tutorial script that might literally bring down your production environment.
Precisely. And Margaret adds another rule specifically for complex systems like concurrency. You have to prompt the AI with what we could call targeted anxiety.
Targeted anxiety.
Yes, don't just ask for a general code review. You have to force the AI to hyperfocus its analysis on the exact areas where the language is most dangerous. Asking explicitly, look at lines 40 through 60. Are there any race conditions in this specific implementation? Have I handled channel closure correctly? Or is there a risk of a go-routine leak if the upstream service drops the connection?
So you are effectively weaponizing the AI's vast knowledge base against your own lack of instinct. You don't know how channels fail, so you make the AI interrogate the channel logic specifically.
Exactly. You guide the AI's attention to the sharp edges of the tool.
Okay, so Timothy has navigated the gauntlet. He used his safety nets. He treated Claude like a tutor. He built his vocabulary in a sandbox. He gave the AI the right scale context. He explicitly asked for jitter. He interrogated the code for race conditions.
He did everything right.
The code is written, compiled, tested, and vetted. It feels like he's crossed the finish line. But there is one final hurdle: submitting this code to the actual human platform team for review.
And this is where Margaret delivers her final and perhaps most psychologically interesting piece of advice before Timothy leaves the library. When he submits this code in a pull request for the team to review, he must explicitly write in the description, I am not a Go developer, do not hide it.
That is a massive plot twist on what we traditionally consider professionalism. I mean, the impulse is usually fake it until you make it, right? Why announce your vulnerability?
If we connect this to the bigger picture, it really comes down to understanding the psychology of code reviews. If you hide your lack of knowledge, and you just submit a highly polished, elegantly formatted, AI-generated file, the human reviewer is going to look at it and assume you are an expert.
Yeah, that makes sense.
They will see the clean syntax, assume you know exactly what you're doing with those weight groups and channels, and they will likely just skim the code for general logic.
They drop their guard, which is exactly what you don't want when you're working with AI in an unfamiliar language. You want them looking for those invisible lifecycle errors we talked about earlier.
Right. So by admitting up front that you don't know Go, you are actively inviting a completely different kind of review.
Yeah.
You are signaling to the reviewer that they need to be hyper-focused.
Wow.
Because you confessed your lack of instinct, the senior Go developers on the team will look at the tricky things, like the concurrency and the channel life cycles, with intense scrutiny. You are essentially recruiting their human instincts to cover the gap where your instincts don't exist yet.
That completely redefines imposter syndrome. Pretending to have expertise you don't actually possess isn't a career strategy. It's a massive liability. It's how subtle, devastating bugs survive the code review process and make it into production.
Absolutely.
Margaret makes it so clear. Working in an unfamiliar language isn't a weakness to be hidden. It's simply a condition to be managed. You manage it honestly, carefully, and by asking for the right help from both the AI and your human colleagues.
It requires a culture of psychological safety, of course. But in a healthy engineering environment, honesty about your own limits is the ultimate mark of professionalism. The AI can write the code, but the humans own the consequences.
So what does this all mean for you? When you are suddenly handed that terrifying file in a language you've never seen, Claude Code can absolutely give you the syntax. It can give you the shapes. But only time, attention, and making mistakes will ever give you the instincts.
Right.
In the meantime, you bridge that gap. You bridge it by leaning heavily on strict tooling compilers that check the AST, race detectors that monitor memory at runtime. You bridge it by shifting your mindset from kicking a vending machine to sitting with a patient tutor. You bridge it by providing deep context about scale and prompting with targeted anxiety. And ultimately, you bridge it by leaning on radical human honesty during the review process.
It's a highly pragmatic approach to a very modern problem.
Yeah.
But, it also raises a lingering question, one that extends far beyond just one junior developer in a library. You talked earlier about the analogy of reading sheet music versus having the instinct, the muscle memory, to actually play the piano.
Yeah, the difference between recognizing a pattern and truly knowing it in your hands.
Think about where this dynamic is heading at a macro scale. If we increasingly rely on AI to instantly translate our logic into languages we don't naturally speak, we're essentially churning out endless reams of sheet music we can't play.
Oh, wow.
How long until our massive global code bases are entirely written in slightly unnatural, purely AI dialects? Dialects that are structurally perfect, grammatically flawless to the compiler, but devoid of human grain? If every developer is just translating concepts through an AI tutor eventually, who actually has the organic instinct to debug the system when it inevitably crashes under load, when everything is a translation, who actually speaks the native language of the machine?
If we're all just reading the sheet music the AI prints out, eventually the music might stop, and we won't know which keys to press to start it again. That is a heavy thought. Next time you're handed a file you don't understand, ask yourself, are you learning the language, or are you just learning how to read the AI's translation? Thank you so much for joining us on this deep dive into the language you don't know. If you found these strategies helpful, please share this with anyone you know who has ever stared blankly at a screen full of completely unfamiliar code. Keep learning, keep asking the hard questions.